second major point in chapter 3 is moment of a force about an axis. And that's what we looked at last time. In order to do that, we had to first study the dot product so that we could create the mixed triple product, which is ultimately what led us to take the moment of a force about an axis. Remember, when we take the moment of a force about a point, we're going to get a vector result. And that vector result would be, or would represent this. If that one point where you took the moment was the only fixed point in the rigid body, the direction of your moment vector would represent the axis of rotation, and then the magnitude would be a measure of the strength of the tendency the force wants to create rotation around that axis. But as we discussed last time, in most rigid bodies, you don't just have a single point that is held fixed. Oftentimes you have an entire axis that is held fixed, like the hinges in the door. So we don't just want to take the moment about a point. What we really want is the moment around that axis that is fixed. So we take the moment about any point that is on the axis, and then we use our dot product in order to get the projection or the component that is in the direction of the axis of rotation. So combining the cross product to get the moment of the force about a point on the axis with the dot product to get the projection, that's our mixed triple product. So that was the second part of chapter 3. Now we're moving into the last part of chapter 3. And the last part of chapter 3 is really this equivalent force couple system. So we're going to have to talk about a little background information. What is a force couple? What's the moment of a force couple? Before we can talk about equivalent force couple systems. We may get to this point today, we may get to this point next week. Okay? We'll just see, how we progress through the first two items here. But those are the three major areas in chapter 3. Moment of the force about a point, moment of a force about an axis, and then equivalent force couple systems. All right, so first thing is we've got to talk about what is a force couple. Well, technically speaking, couple means two, so we're talking about two forces here. And they're not just any two forces, there's something special about these forces. They have the same magnitude, parallel lines of action, but opposite sense. So two forces, equal magnitude, but they point in opposite directions. So we'll say two forces with equal magnitude same line of action and opposite sense. So if we were to draw a force couple, it might look something like this. We would have, let's say this would be the force F heading up and to the right. We'll need a second force, equal magnitude, parallel line of action. So when I say same line of action, I should probably say parallel, because if it was the same, they would lie right on top of each other. So let's call it parallel lines of action. And then opposite sense. So maybe I'll call that one the minus F vector. Okay, it's the same magnitude, but it's just pointing in the opposite direction. Okay, it doesn't have to have the same line of action, but it does have to have a parallel line of action. Now, if you think about what a force couple can do, okay, a force couple is only going to cause a body to rotate. Okay, if you think about applying a force couple to a rigid body, it's going to create some kind of rotation. Translation, remember translation is when the object slides. It changes position from one point to another. So if I just apply a single force, I can get that to translate. But if I apply a force couple, because I'm going to have, let's say, 5 pounds of force going this way and 5 pounds of going force this way, from a translation point of view, they cancel out. But because they're being applied at different points, I do get some rotation. Okay? So the rigid body, it didn't slide, but it did rotate. So force couples, they can only cause rotation. And if they cause rotation, then what we should probably look at is what is the moment of a force couple? Because a moment is something that captures the tendency of a force to create rotation. Well, here we're going to have two forces, so what's the tendency of this force pair, this force couple, to create rotation in our rigid body? So let's look at this in the most general sense, which would be 3 dimensions, and see what we can figure out with our two forces here. So let's see, why don't I just go ahead and draw the 3 coordinate axes with the force couple that we already have. So let's say we have an x-axis, a y-axis, and then z would be coming straight out towards you. Let's say that the rigid body is located somewhere in this 3-dimensional space, and the point where the force that's heading up and to the right is applied, we'll call that one the point A. And let's say the point where the other force is applied is the force B. So what I might do is I might call the force that's applied at A, F sub A. And if I want to call the force that's applied at B, F sub B, I see the relation that F sub B has to be the opposite of F sub A. Okay, so if I want to give it a distinct name, I might call it F sub B since it's applied at B. But it's related to the force at A in the sense that it's opposite, so it's minus F A. And let's say we ask the question, what is the moment of the force couple about the origin? So notice this, it's asking us to find the moment about a point. So we're going to be doing some cross products, some vector products here. Now, if it was just one force, we would just have one cross product. But force couple, we have two forces. So we just find the moment of FA around the origin. We take the moment of the FB around the origin, and we add those two together. And that'll represent the moment of the force couple, the two forces together around the origin. Okay? So let's see what happens here. If we want the moment around the origin, what I'm going to need to do is I'm going to need to take the moment for FA and add to that the moment of FB. Okay, because we have two forces in the force couple. Each one creates or has some moment about the origin. Well, if I add those two together, then I get the total moment for the force couple. So the moment about the origin for FA, well, we would say that's the position of A with respect to the origin cross the force that's applied at A, plus the moment for the force FB. We would just say that's the position of B with respect to the origin cross FB. Now we know something about FB. We said that it's the opposite of FA, so why don't I just make the substitution here and say that we have the position of A with respect to the origin cross FA plus the position of B with respect to the origin cross the opposite of FA. Now, when we talked about the properties of the cross product, we talked about how it's not commutative. We can't reverse the order of the two vectors and get the same result. It's not associative. We can't take three cross products and do the first two cross the third one and then take the first one, cross the last two, and get the same result. We did say it's distributive, though. And another property that we really didn't look at is if you have a constant times one of the vectors, you can pull that constant out of the cross product. So what I'm going to do is this. I'm going to do two things at once. I'm going to take this minus 1, because that's what that negative sign represents, a negative 1. I'm going to pull it out of the cross product, and then I'm going to put it back in with the r vector. Okay? If I can take constants out, then there's nothing wrong with putting constants back in. So basically, I want to get this negative sign with the r, and you'll see why in a little bit. But in order to do that, I factor the negative 1 out, and then I distribute it back in, but I distribute it into the r. So it's going to look like this in the next step. And the reason I wanted to do that is because I now have FA that is common in both of the cross products. And because the distributive property does hold true, I can factor the FA out of these cross products and just get a single cross product. It's going to look like this. I'll start writing here so we can see better. If I factor the FA out, I'm going to have the position of A with respect to the origin minus the position of B with respect to the origin cross FA. So I take the FA out, and what's left? RA minus RB. So that becomes the position vector that I'm crossing with the force vector. Now, one last thing. The position of A with respect to the origin minus the position of B with respect to the origin. We want to look at that one and see if there's any kind of simplification that we can make or any kind of observation we can make related to that vector. So let's see if we can see what this looks like over here. So we have the position of A with respect to the origin. That's this vector. And we have the position of B with respect to the origin. That vector. We also have a vector. Let's call it like this, the position of A with respect to B. And now we see that there's a relationship between these three vectors because they form a closed triangle. Since they form a closed triangle, what that means is this. If I take the position of B with respect to the origin plus the position of A with respect to the respect to B, the result then becomes, if I connect the beginning to the end, the position of A with respect to the origin. So what do we have here? We have, I'll write it over here so we can see how it's going to affect what we're doing inside here. We said if we take the position of B with respect to the origin and then add to that the position of A with respect to B. So that's taking this vector with tip-to-tail method plus this vector. Connecting the beginning to the end, you see the result in is the position of A with respect to the origin. Now just subtract the position of B. Question?
In this case, it looks like the two tails are connected.
So we're taking the position of B with respect to the origin, so that's this one. Okay, so it starts at the origin and it finishes up here. Then I start from that point, drawing the position of A with respect to B. Okay, and then my result, so on the other side of the equal sign, would be what I get when I connect the beginning to the end. Okay, so that's why this vector is coming this way, and you see the two tails. It's because this is the result. Okay, so it's this one plus this one equals, so go back to the beginning and connect it to the end. Okay. So now if I subtract the position of B with respect to the origin on both sides, what do I have? The position of A with respect to B is equal to the position of A with respect to the origin minus the position of B with respect to the origin. So look what I can do with our cross product. I can make one more substitution, one more simplification. I can replace the difference in the two position vectors with the position of A with respect to B vector, and then we have cross FA. So if I want the moment about the origin, for my force couple, I get the position of A with respect to B cross the force at A. Now, look at that result. Okay? Let's see who's really observant. What interesting feature do you notice about the result that we have for the moment of the force couple about the origin? So we have the moment about the origin for the force couple equals this. What is sort of an interesting observation about what you see on the left-hand side and what you see or perhaps don't see on the right-hand side?
It's the position.
What about the position?
The origin. Right. The only thing that.
Okay, so I heard positions and origins. So what's the point of interest related to positions and origins?
I mean, although we're taking the moment about the origin, the thing that affecting is the position of two forces.
Okay, so I think you're definitely going in the right direction. You're about this far away from the bullseye. Maybe somebody can just phrase it in a little bit different way.
Because we know the force are equal and opposite, so the force is going to be constant. The thing that the thing that actually affecting the moment is the position of the two forces.
Right. Yeah, I mean you're right on. So let's put it this way: we're taking the moment about the origin, but does the origin show up anywhere on the right-hand side?
No.
No. It's the position of A with respect to B. Now, would this result have changed if I took my three coordinate axes and just pulled them down this way, so that the origin ended up being down here? Let's just say I drew the x, y, and z axis from this point.
Same thing.
Am I going to get the same result?
Yeah.
Yeah. What if I drew the origin here and had my x, y, and z up here?
Same thing.
Same thing.
Yeah.
So if you think about what's happening here, because it was kind of an arbitrary point that I chose for the origin when I drew my three axes, the moment about the origin, really, we're talking about the moment about any point. Because the right-hand side here doesn't depend on the particular location I chose for the origin, that origin really could represent any point. So what I might do, now that I see this result, is say, what is the moment of the force couple about any point? And instead of calling the point the origin, let me just call it P. So the moment of the force about any point, if you just change all the origins to P's, well, you get the moment about any point. It doesn't depend on the point. So let's say you have a rigid body, and there's a force couple acting on the rigid body. Okay, and one force is acting at A, the other force is acting at B. And let's say there's a third point in the rigid body called C. If you take the moment of the force couple about C, you'll get some result. Let's say there's a fourth point called D. If you take the moment of the force couple about D, you're going to get the same result as when you took it about C. Why? Because the point is arbitrary in this result. Okay? The right-hand side here does not depend on the point, the location of the point that you're choosing. So pick any point, you're always going to get the same result for the moment about the point. Yeah.
Does the plane matters if the points are in the same plane?
Doesn't matter. It's a three-dimensional coordinate system, so that point P could be anywhere in the three-dimensional space, and you'll always get the same result. Okay, we'll do an example in a few minutes. It'll be a two-dimensional problem to help us visualize it a little bit better, but we'll take the moment about 3 or 4 different points, and we'll see that we always get the same result. Okay? So this is an important point, okay? That the moment of a force couple does not depend on the point. So what I might do is I might just even take that subscript out, because if the point doesn't matter, why even bother put it there? The moment of a force couple about a point period is here, whatever the point happens to be. Okay? Whether you choose point C, point D, point E, point F, you're always going to get that same result. So we call this kind of vector, this moment vector that we get for a force couple, we call this a free vector. What that means is we get the same result no matter what point we choose. We get the same result no matter what point we choose to take the moment about. Okay? We started off by thinking of it as the origin, but then we realized that my choice of the origin was kind of arbitrary, and if I had chose the origin to be anywhere else, not only on this board, but anywhere else in this three-dimensional space, even if I had chosen the origin to be right here, and you had x, y, and z axis, I'd still get the same result. So we said, okay, well, it really doesn't represent the moment about the origin, it really represents the moment about any point, and since the location of the point doesn't matter, we just dropped the subscript altogether and said, okay, the moment of a force couple is this. Position of A with respect to B. So the position of where one force is applied with respect to where the other force is applied, cross the force at A. Now you just got to make sure you get your position vector oriented in the right way. If we're going to do this cross product, we have the position of A with respect to B, so that's the vector that goes from B to A, and then we have to cross it with the force that is applied at the end of that position vector. If you try to cross it with the force that's at B, you're going to get the opposite of the result that you should. Okay, so just remember, you can take the position of A with respect to B and cross it with the force at A. If you just kind of switch the letters around, you're going to get the same result if you take the position of B with respect to A and cross it with this force that's at B. Okay? Why? Because flipping the position vector around gives you a minus sign. The force at B is the opposite of the one at A, so you get a negative sign in the position, a negative sign in the force. Those two negatives cancel out, and you're right back to what we have here. Okay, so we're going to see that this is true, that we could take the moment around any point in the rigid body and get the same result. Like I said, we'll do an example where we show that's true for 3 or 4 different points. But before we get there, let me just show you the shortcut to help you out with some two-dimension problems. So if you've got your force vectors, and let's say that they're kind of positioned like this maybe. So here's one of the forces that's in the force couple. This would be the minus one. And let's say you've got the point A and the point B just like we had before. And you've got the position of A with respect to B vector. If I take this position vector and I just slide it down so that its beginning is at the point A, it would be something like this. So I can talk about the angle between the two vectors that are in this cross product as the angle right here, theta. And if that angle is theta, then the angle that would be here would be 180 minus theta, because we've got the straight line for the line of action of the position vector. So it needs 180 degrees. Well, if theta is accounted for here, the rest has to be 180 minus theta. Now if I take a line that is perpendicular to the line of action for F, and connect it up to B. So that's a line like this, and because it's perpendicular, I have a right triangle right here. And let me call that perpendicular line D, or say that it has a length of D. Remember that the cross product, the magnitude is the magnitude of the position vector times the magnitude of the force vector times the sine of the angle that's between them. If I switch the order of the F and the R here, so I end up with F, R, sine, and there's a trig substitution that says the sine of theta is the same as the sine of 180 minus theta. Okay. Verify that one on your unit circle. Okay, here's your unit circle. If I choose this angle theta, the sine represents the y coordinate for this point. If I take 180 minus theta, 180 gets me over here, and then minus theta brings me back up this way. Okay? So 180 minus theta. Notice the y coordinate is the same. Okay, so it's a trig identity that the sine of theta equals the sine of 180 minus theta. So the sine of, or r times the sine of 180 minus theta, or if we just look at the sine of 180 minus theta in terms of the right triangle that shows up here, what do we get? We have here F, the position of A with respect to B, and then the sine is going to be the opposite over the hypotenuse. So that's going to be D over the position vector. So the position vectors cancel and we get FD. So we saw something like this before when we were talking about the moment of a force about a point. And we said that if we take the magnitude of the force times the perpendicular distance from its line of action to the point, we get the magnitude of the moment. Well, when it's a force couple, the magnitude of the moment is the magnitude of one of the forces that's a part of the couple times the perpendicular distance between their two lines of action. And sort of how does that relate to what we saw before? Well, let's say that we have the force couple and we want to take the moment of the force couple about the point B. This force would have a moment about B that is equal to F times the perpendicular distance D. This force has no distance between its line of action and B since the line of action goes through B, so there's no moment around B for this force. So what do you get? For the total, FD plus 0, you get FD. Okay, so it's just an extension of what we've already seen. So that might come in handy when we have two-dimensional